Alright, in section 2.2 we want to talk about quadratic functions, which are functions of the form ax squared plus bx plus c. So what we've done is we added a new piece to a linear equation, the ax squared part, and because of that, that's actually what makes this into a quadratic function. And so some of the things that we want to do today is talk about how to find solutions of quadratic equations, completing the square, which is very important, kind of looking at the shape of parabolas to get an idea of what they actually look like, and the vertex, which will actually be like the bottom of a parabola. Alright, so let's start off first. We're talking about completing the square. So completing the square we're actually going to use for multiple things. One technique for using completing the square is to actually solve an equation. So if I had an equation of the form x squared plus 6x minus 4 equals 0, say, and I wanted to solve it, so this is assuming we've never heard of the word quadratic formula or anything like that. If you tried to factor this, if you remember anything about factoring, this actually does not factor, but at the same time we'd like this thing to actually have a solution. So what we want to do is turn part of it into a perfect square, and then it's going to leave an extra part behind. So the way this problem works is we want to split the x squared plus the 6x, kind of think of it as its own separate problem, and then what we're going to do is we're going to add some number that forces this part to be perfect square. But then, since we want this equation to remain balanced, we have to subtract that exact same amount. So what we're doing here, this is what's called adding a well-chosen zero to a problem. So you're not changing the weight of the problem, it still equals 0, but we're going to use the plus and the minus separately in order to get the answer that we're looking for. And then the minus 4 just comes along for the ride. So the first 3 terms are going to be put together, the last 2 terms are going to be put together, and then from there we can use that to actually solve this equation. So where the box comes from, the number that goes in the box, actually comes from the 6. So to find out what goes in the box, what we do is we take the 6, divide by 2, and square it. That's what gives us our perfect square. So in this case, 6 divided by 2 is 3 squared is 9. So that's what's going to go there and there in our problem. So in this case, we've got 9 and 9 go there. So with that in mind, the first part, the x squared plus 6x plus 9, again, thinking of these guys together, gives us a nice perfect square. This guy will factor as x plus 3 squared, and the minus 9 and minus 14 become minus 13. So finally, to solve, we want to get the perfect square by itself. So if we add 13 to both sides, we get x plus 3 squared equals 13. And the goal is, of course, we're trying to solve for x, so we have to get x outside of that square. So to undo a square, what we want to do is actually take the square root of both sides. Now remember, whenever you take the square root, you always have to attach that plus or minus. Whenever you take the square number, there's always 2 possible right answers. So for example, negative 2 squared is 4, but so is positive 2 squared. So that plus or minus gives us both of those possibilities. So we're almost done. Final thing, now that the x plus 3 is outside the square root, to solve for it, we just want to subtract 3 from both sides. It gives us x equals -3 plus or minus square root of 14. Alright, that's perfect. So that's how we solve a quadratic equation using completing the square. Now what we can do is actually use the quadratic formula in general, or the completing the square in general, to make us be able to solve any possible quadratic equation. So this one, just kind of watch what I'm doing. This can get a little confusing. I wouldn't actually have you do this on a test. But what I'm going to do is generate the quadratic formula from scratch by using completing the square. So generate. So again, I wouldn't have you do this in class, but it is kind of a good exercise to actually see. So what we're going to do is take just some generic quadratic equation and do exactly what we did last time of completing the square, but with no numbers. So this way, when we get our final answer, it'll actually be as generic as possible. So the first thing we have to do is this a is actually going to cause a little bit of problems because we like to have that x squared as a 1 in front. So our first step would actually be to factor the a out of just the first two terms, because remember the c is just going to kind of come along for the ride. So in this case, we're going to factor an a out, so that gives us an x squared. But in the second case, since there's no a, and we have to just divide the a out. And then again, the plus c is just kind of coming along. So on this one, our goal is, again, we want to turn these first two terms into a perfect square. So what we've got to do is figure out what to put in that box, the same way we did last time. So we've got to add something and subtract something to turn this into a perfect square. And so again, it still comes down to the middle term, the term on the x. So I take that b over a and square it. And I end up getting so actually it would be b over 2a squared. Don't forget that you got to divide by 2. So in this case, since the a is also being divided by b, I'll multiply that by 2 as well. So I'll take b over 2a, the whole thing squared, which gives me b squared over 4a squared. And so that's what's going to go in each of these boxes. In this case, I'm going to get b squared over 4a squared minus b squared over 4a squared. And so now, the first three terms makes a nice perfect square, and the minus b squared 4a squared is just going to come along for the ride. So I've got a times x plus b over 2a, whole thing squared, minus b squared all over 4a squared plus c. Now I need to combine these two guys together, but unfortunately the minus b squared over 4a squared is all sitting inside the parentheses. So what I need to do is actually go ahead and factor this a so I can combine these outside guys. So if I bring that a in, I'm going to get a times x plus b over 2a squared minus, so a times this is actually going to get rid of one of these guys. So I'm going to get minus b squared over 4a plus c. so again, let's make a little common denominator of these last guys. X plus b over 2a squared. So if I make these guys have a common denominator, and multiply top and the bottom by 4a, so we have minus b squared minus 4ac all divided by 4a. This whole thing in parentheses in this case. And if we remember, this whole thing was originally set equal to 0. So if we actually start to solve, so we're going to run here. It's a long problem, that's why I said I wouldn't make you do this on a test. So we're going to actually add this whole thing to the other side. So now I've got a times x plus b over 2a squared equals b squared minus 4ac over 4a. We'll divide by a, which is going to make this into an a squared on the bottom. So finally I've got x plus b over 2a squared, b squared minus 4ac over 4a squared. Again, if I want to get the x plus b over 2a outside the parenthesis, out of the square, I just want to square root those sides. So I get x plus b over 2a equals plus or minus b squared minus 4ac all over. So we'll simplify the bottom, since the bottom is a perfect square, so 4a squared is just 2a. And finally subtract b over 2a from both sides. Gives us x equals negative b plus or minus square root of b squared minus 4ac all over 2a, which is our quadratic formula, which you may have actually seen before. So again, the quadratic formula is going to be a nice handy way to find solutions of a quadratic equation. Alright, so let's see how we can actually use the quadratic formula. Oops, wrong way. To find some solutions. And so the good thing is quadratic formula is going to work every single time. Like anytime you try to solve an equation, you're going to be able to find answers. That's the good thing. So if I had, for example, x squared minus 7x plus 8 equals 0, and I wanted to solve this using the quadratic formula, then what I have to do is just first identify the different pieces. So the a is the coefficient in front of the x squared, the b is the coefficient in front of x, and the c is the coefficient in front of 8. So in this case I've got a equals 1, b equals negative 7, and c equals 8. So when I plug them into my formula, I've got negative b plus or minus b squared minus 4ac all over 2a. So negative 7 is actually going to be a positive 7 plus or minus negative 7 squared minus 4 times 1 times 8 all divided by 2 times 1. So it's 7 plus or minus 49 minus 32 over 2. Minus 32 is 17 over 2. And then finally, that's actually as good as I can get. Since square root of 17 doesn't reduce any further, that's actually as good as we can hope to do. for this problem, so you can just stop right there. Or if you wanted, you could separate it as 7 plus square root of 17 and 7 minus square root of 17. But either way, that one's actually perfect. All right. So again, that was much easier than having to complete the square and things like that. So there are some major advantages to being able to use the quadratic formula to solve equations. So another thing that's kind of nice is you can actually, using the discriminant of the quadratic formula, which is the b squared minus 4ac, it's the part underneath the square root. By using that, you can actually predict what kind of solutions you're actually going to expect to get. So, because the idea is, since that guy's underneath the square root, if we ended up with negative numbers, that would actually be bad. It would give us things called imaginary numbers, or another way to think of it would be no real solutions. So what happens is, the discriminant's actually broken up into 3 different cases. B squared minus 4ac is less than 0. B squared is minus 4ac equals 0. And b squared minus 4ac is greater than 0. So again, in the first case, that would give us a negative number inside the square root, which would give us, imaginary numbers. But for our cases, what we're really interested in is the fact that it's going to give us no real solutions. Now, in the second case, if b squared minus 4ac equals 0, so remember our formula is x equals negative b plus or minus b squared minus 4ac all over 2a. If this whole thing is 0, then notice all that's going to be left is just negative b over 2a. So in this case, we're only going to get one solution with x equals negative b over 2a. And finally, in the last case, when b squared minus 4ac is greater than 0, then a positive number inside the square root is actually fine. And so this is going to give us 2 real solutions. And our answer, of course, is going to be the negative b plus or minus square root of b squared minus 4ac all over 2a. So it gives you kind of a check to go in, because before you actually do a problem, you could always try the discriminant. And if you know you're going to get, say, imaginary numbers, for example, then there's no point in even going through the whole process of trying to find the quadratic formula to get imaginary numbers. Same thing if it would happen to reduce down to 0, then you'd know right away that my answer is going to be negative b over 2a, which is both kind of nice. Alright, so another way to actually use completing the square, or that form, is to find the vertex of a parabola. So if we look at a parabola has a shape that's either, it's kind of a U shape, it either points up if it looks like that, and it points down if it looks like that. And so at the bottom on the left or the top on the right, those 2 points are called the vertex of the parabola. So a parabola points up like the one on the left if the leading coefficient is positive, and a parabola points down if the leading coefficient is negative. And the vertices in this case, we've got our vertex here and here. They're really nice. They come in handy for word problems and things like that, because on the left, since the parabola points up, the vertex, in this case, whoops, sorry, the vertex is the smallest value to ever occur, and the one on the right is the largest value to occur. So that's going to come in handy when we're actually trying to find like domain and range and things like that. If you think of it from for a quadratic equation, unless the domain is restricted, the domain is going to be all real numbers. So for a quadratic formula, quadratic equation, the domain is all real numbers. And what's going to happen is the vertex is actually going to tell us what our range is. Because if our parabola is the one on the left, then our range is going to start at the vertex and go up to positive infinity. Or if it's the one on the right, then we're going to go from negative infinity up to that vertex. But I'll show you in 1 second when we do a little problem. So let's actually use the quadratic formula, or use completing the square to actually find, the vertex. So let's assume we're looking at x squared plus 6x plus 11, and we want to find the vertex of this guy. So the goal is, what we're actually going to try to do is put this into what's known as the vertex form of a quadratic, which is a times x minus h squared plus k, where h comma k is the vertex. So it's nothing more than completing the square. We've already been doing this. So in our case, luckily we don't have an a, so we don't have to deal with that. So right away, we can take this guy, add our plus square, minus our square, do our plus 11. Again, we need to figure out what goes in the square. So take your 6 divided by 2 squared. So again, this gives us 9. So in the first case, this guy factors as a perfect square, x plus 3 squared, and negative 9 plus 11 gives us a plus 2. So now we've got our function in the vertex form. So what this means is that on the inside, notice we always take the opposite of the sign. So it was a minus 8, so we actually took an 8. So since we have a plus 3, we want our x-coordinate to be a negative 3, and the outside just stays the same. So we look at the negative 3 comma 2 for our vertex. Since our a is equal to 1, which is greater than 0, our graph points up. So even though we don't know exactly what it looks like, we could roughly say, at negative 3, you got a vertex there, and it's going to have some kind of a shape like that, pointing up. Again, you can put this in your calculator, you get a much more accurate graph, but that gives us a rough idea. So from there, the nice thing is I could say, well, what's the domain of this quadratic function? And of course, it's going to be all real numbers, so it's going to be negative infinity to infinity. Now the range, on the other hand, since this guy is actually pointing up, this is going to be the starting point of our range, and then from there it goes to positive infinity. So our y-coordinate is either going to be the starting point of our range or the end point of our range, depending on whether the graph points up or down. So in this case, since we start there, we're going to get square bracket 2 up to positive infinity. If this graph would have pointed down, then our range would have gone from negative infinity up to 2 in that case. So, all right, does that make sense? Everybody all right there? All right, very good. Well, those are the things that I really want you to know most out of 2.2. Now, there are some other important things in 2.2, and I would like you to read those on your own, even though you won't actually be tested on them. But what they are is conic sections, which is a collection of different types of graphs that come up very in lots of different areas. Some of them are non-functions, which is one of the reasons we don't do a lot with them, but that doesn't mean they're not important. So like starting on page 154 in the book, they give another blurb about parabolas, because a parabola is a conic section. But then from there, they go into circles and a little bit about the equations of circles. And it would be good to know how to identify the equation of a circle. An ellipse, which is kind of an elongated circle. And again, they talk about the equations for ellipses, some foci, some different things, and then finally hyperbola. So again, I do want you to read those on your own, just mostly for information purposes, because these are formulas or functions, non-functions, that you should actually know the equations of by sight, and things like that. So again, we won't be actually testing on them or anything, but it will be very handy. So that's 2.2, and that's the things from there. So if I get a chance in a little bit, I'm going to try to do a little video for 2.3, which is just involving exponents and things like that. So it should be a little bit easier and quicker. This was pretty intense with completing the square. So feel free, if you have any questions, definitely let me know, and I'll try to put up any kind of video that you might need to help. Otherwise, have a good rest of your snow weekend, and hopefully I'll see you guys on Tuesday.